Hello everyone, welcome to the course Structure Analysis. Myself, Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the 9th lecture of Structure Analysis. In this lecture, we are going to discuss how to draw the shear force and bending moment diagram for the problem which we are discussed in lecture 8. So in last lecture, we are calculated the end moments of the continuous beam using a slope deflection method. So in today's lecture, we are going to discuss how to draw the shear force and then bending moment diagram. So this is the 9th lecture. At the end of the lecture, you can able to calculate the reaction forces of a continuous beam and also draw the shear force and then bending moment diagram. So simply I am going to take the beam which we are already discussed in the last lecture. Let's draw that beam. So this is the problem. In last class we are discussed, which is having two spans. The first span is having the 50 kilonewton load, and then second span is comprises of the UDL, which is 24 kilonewton per meter. Each span is 5 meter. Each span is 5 meters. And this is 2 meters, 3 meters. Let's mark the support A, B and then C. So already we computed the moments. So let's write those moments, the end moments which we are calculated. So support A, we are calculated, the moment is 29.5 kilonewton meter, and then at support B, it is 37 and then 37. At support C, we computed already, it's 56.5 kilonewton meter. So in a fixed beam or continuous beam, in order to calculate the reaction forces, first we should know the end moments. So by using a slope deflection method, we are already calculated the end moments. Now we are going to draw the shear force and then bending moment diagram. So for a simplification, we will go span by span. First I am going to consider span AB. I am going to consider the span AB. So I am just going to draw the span AB alone here. So in the span AB, just to consider all the fixed supports because we computed the moment, and then mark that moments. So this is 29.5 kilonewton meter and this moment is 37 kilonewton meter. So 29.5 and then 37. Span 5 meters. And then the point load is 50 kilonewton and this is 2 meter distance and this is 3 meters distance. Let's mark the supports, support A and then support B. Now I am going to take the moment at support B. Taking moment at support B. So before that, we can fix the notations. For example, if it is a clockwise moment, I am going to consider positive. If it is an anti-clockwise moment, I am going to consider negative. Okay. So this is the standard conventions we are using. Otherwise, we can equate the clockwise couple and then anti-clockwise couple also. So both the things I will explain. So when we are discussing about the next problem, we will equate the clockwise couple and then anti-clockwise couple. Okay. So currently I am considering these symbols. Now I am taking moment at B. I am going to interested to calculate the value of RA. So you can see the moment is force multiplied by the perpendicular distance. We going to have the reaction at support which is RA. So RA multiplied by the perpendicular distance is 5 meters. Okay. And then there is a load acting downward direction which is minus 50 multiplied by the remaining distance 3, perpendicular distance 3. Okay. And then what are the other things are there? We have a 37 kilonewton which is clockwise couple. You see here, which is, we have a 37 kilonewton which is a clockwise couple. So I am substituting that value, that is 37 equal to 0. So if you simplify this, we will be getting 5 RA equal to 142.5 by 5, which is 28.5 kilonewton. Okay. So we calculated the value of RA. Now we need to calculate, we need to take the equilibrium equation, summation of all the vertical forces is equal to 0. So in the beam, if you see, this is our beam. Here we have a RA value. Here we have a RB1 value. Why RB1? Because it's intermediate supports. We need to calculate RB1 and then RB2. Okay. So, and then we have a point load here which is 50 kilonewton. Now I am going to sum up all the vertically upward and downward forces. Vertically upward I am going to consider as a positive, and vertically downward I am going to consider as a negative. So RA plus RB1, force is acting downward, so minus 50 equal to 0. So just I am going to substitute the calculated value RA, which is already we are calculated, 28.5 plus RB1 minus of 50 equal to 0. So the RB1 is nothing but 50 minus 28.5. So RB1 is equal to 21.5 kilonewton. Okay. Similar way we need to calculate the RB2 also. Now, so we calculated the value of RA and then RB1. Now I am going to take the support, I am going to consider the span BA. I am going to consider the span B and then C. So in the span BC, UDL is there, whose intensity is W, the W per meter. The given load is 24 kilonewton per meter, 24 kilonewton per meter. Okay. And this span is 5 meters. Now let us calculate this value also. And in previous slides, we have the BC moment is 37 and 56.5. So this is 37 and this is 56.5 kilonewton meter. So we have a RB2 here, RB2. Now what I am going to do, I am going to take the moment, at point C. Okay. So here one more moment will come, we forgot to include it, because you see the 37 is a clockwise couple and then we forgot to incorporate the anti-clockwise couple, which is 29.5 has to come before this equal to. So then only we will get this value. Now taking moment at the point C, RB2 and then the linear distance is 5 minus 25 multiplied by 5, since it is a UDL, 5 by 2, at center it will act, and then the clockwise couple is 56.5, okay, and then the anti-clockwise couple is minus 37. Anti-clockwise couple is minus 37, B and C. Yes. So we will be getting RB2 is equal to 280.5 divided by 5, so which is 56.1 kilonewton. I'll explain once again. So RB2 force into perpendicular distance is 5 minus 25 into 5 into 5 by 2 plus 56.5 is a clockwise couple, and then the anti-clockwise couple is minus 37, okay. So equal to 0. Actually equal to the moment at C, we are considering that is also inside, okay. So we got the RB2. So next I need to use the equilibrium equation, summation of all the vertical forces are is equal to 0. So here you see RB2 vertically acting in upward direction, then RC also vertical direction, okay, and then the load given is minus 24 multiplied by minus 24 multiplied by 5, minus 24 multiplied by 5. So this will give me RC is equal to 120 minus 56.1, 120 minus 56.1. So RC is equal to 63.9 kilonewton. So we have calculated RB2 and we have calculated RB1 also. So RB is nothing but RB1 plus RB2, okay, RB1 is 21.5 and RB2 is 56.1 kilonewton. Adding this, we'll be getting RB is 77.6 kilonewton. So this is the value of RB. Now quickly we draw the shear force diagram. Let's calculate the shear force value. For that, once again I need to draw the beam and then mark all the reaction forces we are calculated. So we have the RA is 28.5, RB is 77.6 and RC is 63.9 kilonewton. And then let's mark the load also. This is 50 kilonewton for span AB, 2 meters, 3 meters, and span BC we have the UDL of 24 kilonewton per meter. And mark the supports. This is A, B, C and this is D. Let's calculate shear force at the point C is minus 63.9 kilonewton. So whenever we are going from right to left, we consider the first value is negative. So we are doing the reverse process. If you go to A to C, then we consider all the downward forces are negative and upward forces are positive. So here I am going to consider all the upward forces are negative and downward forces are positive. Okay. So shear force, what is the next point? The shear force at right of B, shear force at right of B. So minus of 63.9, at right of B we are having minus 24 into, and then the distance is 5 meters, okay, 5. So we will be having 56.1 kilonewton. Now shear force at the point B exactly 56.1. At point B we have a support reaction of 77. Upward I consider negative, so 77 minus of 77.6. So we will be getting minus 21.5 kilonewton. Then shear force at the point D equal to minus of 21.5 plus 50, which is 28.5 kilonewton. And shear force at the point A 28.5 and upward we have minus of 28.5, it will become 0. So exactly it will come and end up with a 0. So let's quickly draw the shear force diagram. First you need to draw the straight line and mark this is A, D, B and then the point C. Okay. So now mark the values. At point C we have minus of 63.9 kilonewton. At point B we have positive 56.1 kilonewton. At the point B another value is minus 21.5, and point D we have 28.5 kilonewton. Okay, so let's connect this. This is coming down from the C, and then from the point B to C we have a UDL. So you need to connect it by a straight line like this, and then all the way it is coming down. From the point B to D we don't have any loads, so linearly horizontally this line has to go, and connecting like this. This is positive, positive, negative, negative. So this is your shear force diagram. Let's quickly discuss about the bending moment diagram. So first to take the beam. Okay, so this is 50 kilonewton. Throughout the span UDL whose intensity is 24 kilonewton per meter. Both the spans are 5 meters. This is 2 meters and this is 3 meters. And mark the support A, B and then C. Okay. And then I am going to mark these moments, which is 29.5 plus 37, 37 and then 56.5 kilonewton meter. So just draw the bending moment diagram. So I am going to draw the bending moment diagram by superposition method. For that, what I am going to do, I am going to consider these beams are simply supported and then going to draw the bending moment diagram. If I consider the beams are simply supported, then the beam is going to like this. The beam is going to be like this. 50 kilonewton, 2 meters, 3 meters throughout the span UDL, which is 24 kilonewton per meter. A, B, C. 5 meters, 5 meters. Let's draw the maximum positive bending moment diagram. For this, the bending moment diagram is triangle. For the next diagram, the bending moment diagram is a parabola or semicircular arch. Okay. So now what we are going to do, we are going to calculate the maximum positive bending moment. Since it is a span AB, the load is eccentric. We need to put WAB by L. This is a formula to compute the eccentric load, maximum bending moment. So this is going to give you, if you substitute the 50, I will substitute it here, 50, and this is the A value and this is the B value. So 2 multiplied by 3 divided by L is 5, we will be getting the value 60 kilonewton. But for this, the maximum bending moment is WL square by 8 for a UDL. So W is 24 and the span is 5 meters divided by 8 will give you 75 kilonewton meter. It's going to give you 75 kilonewton meter. Now I am going to draw the support moments diagram. So at A I am having, this is 29.5 kilonewton meter, and at support B I have 37 kilonewton meter, and at support D I have the maximum of 56.5 kilonewton meter. So here there is no sufficient space. Let's draw this diagram in the next page. So this is the moment diagram. and this ordinate is 29.5 and this is 37 and this is 56.9. Okay, let's join these ordinates by the horizontal line and then you can eliminate this line. This is not required. Okay. So now we are going to superimpose the positive bending moment diagram which you are already drawn. So this ordinate is 60 and this is, I hope it is 75, yeah, it's 75 kilonewton meter. And then I will mark our bending moment diagram. So this portion is our bending moment diagram. So we got our bending moment diagram by superposition method. So bending moment diagram. So in this lecture, we are discussed about how to draw the shear force and then bending moment value for a continuous beam. So in the next lecture, again we are going to discuss the another problem. So in this lecture, we are discussed how to draw the shear force diagram and then bending moment diagram for continuous beams. In next lecture, we are going to discuss the another example problem. In that, we are going to once again calculate the shear force and bending moment diagram. Thank you for watching this lecture. Thank you.